Okay. Our last speaker of the session is Rory Lucyshyn-Wright, and he will be talking about weighted pullbacks in V-graded categories and universal quantification in V-actegories. The floor is yours.
Thanks. Thanks very much for inviting me to speak. So I'll be talking about something nice and simple and quite easy, but I think it's of some importance. So we'll start off by reviewing something quite simple, namely simple products and universal quantification. And specifically, this will be a special case of the categorical approach to quantification that was introduced by Levere in the paper Adjointness in Foundations. And also, you can consider a nice text on this sort of material, but going much more in a much more general setting, is the book by Jacobs. So let's say we start with two objects, X and A, of a category C with finite products. Then given a morphism, Q, from some object, capital Q, into the product, X times A simple product of Q is a morphism of the following form. So it has a domain. The domain object of this morphism will write as capital Pi subscript X of Q. And we're thinking of that as a product of fiber-wise product of indexed families of objects, which this will become clear in a moment. So it's an object, pi x of q, equipped with a morphism little pi down to A, which we're thinking of as a projection down to A. And this morphism is required to be equipped with a co-universal arrow in a certain sense. So to understand this, we'll regard pi x of q as an object over A. So an object of the slice category over A. And as such, we want to equip it with the structure of a co-universal arrow written in the following way, epsilon, going from x times pi x of q to q, co-universal arrow for the following functor. It's the functor from the slice category C over A to the slice category C over the product, x times A. And this functor is given by just taking the product with x. So we want to ask for a co-universal arrow for that. So this is quite a brief way of putting this. But you can see that in particular, one of the data, the part of the data for this is a morphism epsilon of the given form in actually the original category C. And if C is Cartesian closed and has finite limits, then C does have simple products. We can always construct the simple product. We'll actually see a recipe for how to construct it in a more general setting later in the talk. And the simple product of a monomorphism, Q, is again a monomorphism that we write in the following way: for all xq, it's a subobject of A. So, and this we call the simple universal quantification of Q. So you can see that what's happening is that we start with a subobject of x times A, then we sort of get rid of the x and get just a subobject of A, because we're actually, in a sense, universally quantifying away the x. And we'll see that in an example, the basic case of C equal to set. Then the simple product, when we look at the map pi from the simple product down to A, we can look at its fibers, because the whole point of view is that, we're thinking of a map as a index family of sets, namely the fibers of the map. So let's look at the fibers. We look at the fiber pi inverse of A over a given element A of A, and it can indeed be computed as the product over all x in X of the fiber over the pair x times a. So this is why we're producting away the x, in a sense, in this classical case. And also, if Q is a subset of x times a, then when we take the simple universal quantification for all xq, it's now a subset of A, and it's the set of all little a in A such that for all x in X, the pair x comma A is in Q. So this is why indeed this is given by the for all quantifier in this case of set. All right. So we've reviewed this material which originates with Levier, and it's a special case of Levier's ideas. But now we're going to move to, in a sense, a more general setting involving monoidal categories. So namely, we'll look at V-actegories. So let's review what a V-actegory is. Let V be a monoidal category. Then a left V-actegory is a category C equipped with a strong monoidal functor from V into the category of endofunctors of C, regarded as a strict monoidal category. And we're going to regard this as an action. It's a strong monoidal functor whose transpose, which is a functor from V times C to C, we write as a left action. So we write it as sending each pair of objects x comma a. So x being an object of V and a being an object of C, we write the value of as x dot a. So that this is written as a left action. So for example, we can always regard V itself as a left V-actegory, where we have x dot a being defined as the monoidal product, x tensor A, for each pair of objects x and a of V. And this is great because we can't always regard a monoidal category as enriched over itself, but we can regard it does act on itself, so we can regard it as an actegory. And then we can form a two-category of V-actegories, where as the one cells, we take lax morphisms of actegories. So those are functors between actegories that are equipped with data that witness the lax preservation of the action. And the resulting two-category we're going to write as V-act in this way. Okay, so at this point, we'll introduce a new concept called a weighted pullback, and we'll start off by introducing this in V-actegories, but then we'll generalize this to a more general setting later in the talk. So as a definition, let C be a V-actegory. Given an object x of V and a pair of morphisms in C of these special forms, so let's take a look, F going from x dot A, that we're applying the action there, x dot A to B, and then we have Q being just an ordinary morphism, just an arbitrary morphism, from some object Q down to B. So we can think of that as an object over B, over the codomain of the first morphism, right? And then we're going to conceive of sort of pulling this back in a sense. We're going to conceive of pulling this back in a way, but we're going to pull it back over A. So the sort of notion of pullback that we introduce, which is called a weighted pullback, it's going to be an object over A, actually. So an x-weighted pullback of Q along F is an object P of C equipped with morphisms of the following forms. So P is going to be equipped with a morphism down to A. So P is an object over A, as I mentioned. And we'll ask also for a morphism F prime from x dot P to Q, which we can also think of as in a certain sense, analogous to a pullback of F. These are required to make the following diagram commute. So we can take a look at the diagram. On the bottom and the right, we have the given morphisms. And as in a pullback, we're asking for to turn this into a square. But you can see the form is a little bit different because we have this x dot on the left. We ask for this diagram to commute. And we also ask that the given morphisms P and F prime are universal with this property. So what does that mean? i.e., for all morphisms little r from an object R down to A, so any object over A, and any G from X dot R to Q, with the equation holding here, we could write that again as such a commutative diagram. We require a unique induced morphism. There is a unique T from R into P, P being this weighted pullback object, satisfying these equations. So nice, simple, direct, universal property as we would write down in basic introductory category theory. But you can see that this is a bit different from a pullback because we're throwing in the object X. Where does that live? That's an object of V. Okay, so here's a theorem. Let C be a V-actegory. And let's say we suppose that C has pullbacks, ordinary pullbacks, and each functor X dot blank has, from C to C, has a right adjoint. So here I should be a bit more explicit and say for each object X of V, right? For each object X of V, the functor X dot blank from C to C has a right adjoint, which we're going to write as blank to the power X, which makes sense. Generalizing, for example, the notion of exponential in a monoidal category. So yeah, so in particular, generalizing the left closed Hom in a left closed monoidal category. Okay, so under these circumstances, then C has weighted pullbacks. We've assumed that it has ordinary pullbacks and also these adjoints. Then C has weighted pullbacks. We can construct them. Explicitly, the weighted pullback of Q from Q to A along F from X dot A to B can be constructed as the pullback taken in the following way. So you can see that we take F tilde down the bottom there. That is the transpose of the given morphism F. It lands in this power b to the x. We apply that power process to little q. That's what we have on the right. Pull that back, we get actually a weighted pullback. Okay. So for example, if the monoidal category V is left closed and it has ordinary pullbacks, then when we regard it as a V-actegory, the V-actegory C equal to V has weighted pullbacks. Now we come to our generalization of simple products, which we had seen at the beginning of the talk. We'll generalize these to the context of V-actegories. As a definition, in a V-actegory C, a simple product of a morphism Q from Q into X dot A, simple product with respect to X in objects of V, X being an object of V. So you can see what's changed now. Instead of having X times A in the codomain, we have X dot A, we're actually using the action. And how are we going to define this? We'll define it as a special case of weighted pullbacks. This is an X-weighted pullback of Q along the identity morphism. Okay, normally pullbacks along identity morphisms, well, it's the same morphism. But here this is a weighted pullback, so we're involving the identity morphism, but we're taking an X-weighted pullback. So when we pull it back, we get something over A, actually. So this is equivalently a morphism pi from an object capital Pi x of Q. We're introducing this notation here, generalizing the concept that we'd seen earlier, a morphism down to A, equipped with this time a co-universal arrow of the following form. So it's a co-universal arrow, this time for the functor x dot blank, going from C over A to C over X dot A. So just straightforwardly generalizing that formulation as a co-universal arrow, but now with respect to the action rather than taking products X times blank. Okay, and this is indeed an equivalent way of characterizing the weighted pullback of Q along the identity morphism, as we've mentioned. Now, the simple product of a monomorphism, Q from Q into X dot A, we can again show that this is a monomorphism, and we'll write it as for all X, Q, sub-object of A, and we call this the simple universal quantification of Q. So let's pause to think about this for a moment. We're in an actegory, C, and we have these objects an object A of our actegory, but then we have an object X of V, and we're sort of quantifying away that object X of V. Okay, as an example, we can recover what we had earlier in the classic case. When V is a Cartesian monoidal category and C is taken to be V, we recover the familiar notions from earlier of simple product and simple universal quantification. But we should have new examples also. So for example, if the monoidal category V is left closed and has pullbacks, then we know we can form weighted pullbacks. So we can form simple products. Then in C equal to V, a simple product of a morphism of the following form from an object Q into the monoidal product, X tensor A, can be constructed as the following pullback. So as a special case of the recipe we'd seen earlier, we just put the co-evaluation on the bottom of the square and take the pullback in this manner. This gets us a simple product. And, this generalizes the recipe that we have in the Cartesian case, but now we can do this in a monoidal category. When it's left closed, these certainly exist. And when it's left closed and has pullbacks. All right. So we can apply this to familiar examples of monoidal categories. We can take C to be V to be the category of abelian groups and see what we get. Then the simple universal quantification of a subgroup Q of the tensor product of two abelian groups, X and A, is the following subgroup. For all xq, what it ends up being is the subgroup consisting of all the elements A of A, such that for all, we're seeing that for all again, for all x in X, the pure symbol X tensor A is in Q. Okay, so we get a kind of monoidal variation on the notion of universal quantification for subobjects. Okay, now here's a general theorem about the sufficiency of pullbacks and simple products for forming weighted pullbacks. In a V-actegory has weighted pullbacks if and only if it has pullbacks, ordinary pullbacks, and simple products. Recalling that simple products are also a special case of weighted pullbacks. And so in this case, how we prove this is that the weighted pullback of Q along F from X dot A to B, it can be constructed in the following way. It can be constructed as the simple product of the pullback of Q along F. So first we take Q, pull it back along F, that gets us something over X dot A, and then we product away the X, and this works. So V-actegory has weighted pullbacks if and only if it has pullbacks and simple products. Now, so far we've talked about actegories, and actegories are in a way related to enriched categories. So we'd like to have these concepts apply also to enriched categories. So let's take a look at enriched categories. V is not symmetric here, so we'll have to adopt one of two conventions in a sense. So we'll adopt the convention that a V category C, or a left V category, as I like to call them, has composition morphisms of the following form. So the composition morphisms are in V, and they go from script C, B comma C, tensor script C, AB to script C, AC. This is one of two conventions. This is sort of the non-diagrammatic order in a sense, we could also instead ask for the diagrammatic order that's different since V is not symmetric. Then we can form the two category of V-enriched categories, VCAT. So as far as examples of V-enriched categories, of course, there are lots, but a very basic example is that if V is biclosed, then certainly V underlies a V category. Now, we'll now move to a setting that encompasses both actegories and enriched categories as instances, in a sense, of an overarching concept, the notion of a V-graded category. So first we'll give an abstract definition of this. A left V-graded category, C, is by definition a left V-hat category for the base of enrichment V-hat obtained in the following way. V-hat, that's the functor category from V up to set being here the category of large sets, and we're equipping this functor category with the day convolution monoidal structure. So categories enriched in V-hat, we call them V-graded categories. And these have been studied by a number of authors. They were introduced by Richard Wood and have been studied by Kelly, Labella, Schmidt, and Street, and Paul Levy, Richard Garner, McDermott and Ustalu, and me in a recent paper. And we can form a two category of these, of course, because it's the two category of V-hat enriched categories. Okay, this is a succinct abstract definition, but then we can unpack the data for a V-graded category and form an elementary definition. Equivalently, a V-graded category C consists of the following data: a large set, ob-C, of objects. And for each pair of objects, A and B of C, and each object X of V, we ask for a set that we write in the following way. It looks a bit like a Hom set, but it sort of has two input objects in the domain position, in a sense. X is an object of V. And the elements of this set we write in with the following notation: F going from X comma A to B, just a formal notation for sort of those two objects involved in the domain. F from X comma A to B. And we call these graded morphisms from A to B with grade X. And then we want to be able to compose graded morphisms. So we ask for an assignment to each pair of graded morphisms, F from X comma A to B, and G from Y comma B to C. So you can see the A and B and C, well, those look like they're composable, but we have these two different grades, X and Y, thrown in. So we ask for a graded morphism, the composite G of F, whose grade is the monoidal product Y tensor X. And then we want identities. They'll be graded morphisms whose grade is the unit object I of V. So we ask for graded morphisms I sub A, going from I comma A to A for each object C of C. And we need something more, an assignment to each graded morphism F from X comma A to B, and each morphism alpha in V from Y into the grade. So the grade is X, right? But we've got some morphism alpha in V going from some other object Y into X. We're going to sort of pull back or reindex the graded morphism, pull it back to something with grade Y. So we ask for a graded morphism alpha upper star of F with grade Y from A to B that we call the reindexing of F along alpha. And so this corresponds to the action of the Hom presheaves on morphisms with reference to the abstract formulation that we just saw. We're going to require that these data satisfy some axioms, which I'll go through very briefly, satisfying the following axioms: functoriality of reindexing. This reindexing is required to be functorial in the following sense: contravariantly functorial. Composition is required to be natural with respect to reindexing, so that amounts to this equation here for all graded morphisms F and G of these forms. composable, and then every pair of morphisms alpha and beta in V of these forms. So we have a compatibility of composition and reindexing. Then we have an associativity of composition, but it shows up as being associativity up to reindexing, up to a certain reindexing. So if we have three composable graded morphisms, then when we look at this composite, it's the reindexing of this other parenthesized composite along the associator. And then an identity axiom, a central identity for every f from x comma a to b in C. When we compose with an identity, this is the reindexing along the right uniter. The reindexing of f along the right uniter. And if we compose with the other identity IB, that is, again, the reindexing of f along a uniter, the left uniter this time. So we have this concrete but more lengthy formulation. Now, every V-graded category has an underlying ordinary category. What are its morphisms? We just declared that a morphism f from A to B in a V-graded category C is a graded morphism of grade I comma A to B, whose grade is the unit object I of V. So we have a notion of ordinary morphism, and so every V-graded category C has an underlying ordinary category C naught, and we can say that it has the same objects and morphisms as C, given this notion of morphism in C that we've just defined. Okay, so V-actegories give us examples of V-graded categories. Every V-actegory can be regarded as a V-graded category with the same objects, in which a graded morphism f from x comma a to b is simply a morphism. We use the action, a morphism from x dot a to b in the category C. Thus, we obtain a fully faithful two-functor from the two category of V-actegories to the two category of V-graded categories, allowing us to regard V-actegories as a special case of V-graded categories in a sense. And the essential image consists of those V-graded categories that have copowers x dot a by objects of V. So x in ob V and a in ob C. For example, V itself is a V-graded category because it acts on itself. So in V, a graded morphism f from x comma a to b is simply a morphism f from x tensor a to b in V. So that's how we can always regard V itself as a V-graded category. And, this is great because we can't always regard V as a V-enriched category. Because V is not assumed closed here. But we can regard V as a V-graded category. Now, also V-enriched categories give us examples of V-graded categories. Every V category C can be regarded as a V-graded category with the same objects, in which a graded morphism f from x comma a to b. Now we'll have to do something a little different. We define f to be a morphism in V from the grade x into the Hom object because we have a Hom object script CAB in V, a generalized element of the Hom object, so to speak. In this way, we obtain a fully faithful two-functor from the two category of V categories to the two category of V-graded categories. So we can also regard enriched categories as V-graded categories. Now, one useful technique for working with V-graded categories is the enveloping actegory. Let C be a V-graded category. Then there's a V-actegory that we write in this way, V comma C, equipped with a fully faithful V-graded functor from C into it. So we're embedding a V-graded category C into a V-actegory. And actually, this has a universal property because the canonical two-functor from the two category of V-actegories with strong morphisms of V-actegories, so preserving the action up to isomorphism, specified coherent isomorphism, the canonical two-functor from there into V-graded categories has a left biadjoint provided by this construction, so whose unit consists of the above embeddings of V-graded categories into V-actegories or into the underlying V-graded category of a V-actegory, V comma C. So we introduced terminology. We call V comma C the enveloping actegory of C, and we identify C with a full V-graded subcategory of its enveloping actegory under this embedding, of course. And we now start to write the left V action on this V-actegory, this larger V-actegory, as a comma, because then every object of V comma C is isomorphic to X comma A for some object X of V and some object A of C. And then graded morphisms in C, which we already had a notation for, they're actually equivalently given by morphisms of this form, F from X comma A to B in the larger actegory, where now we're writing X comma A as the result of applying the action in this larger actegory. So these 2 points of view and notations line up and are consistent with each other. We've embedded each V-graded category C into a larger actegory, and we can therefore work in this larger actegory. And this is useful because we can now use diagrams in that larger actegory, which I call envelope diagrams. Composition and reindexing in a V-graded category C can be depicted using commutative diagrams now, commutative diagrams in the enveloping actegory, V comma C. We call these envelope diagrams. So here are some examples given graded morphisms F and G that are composable, and also a morphism alpha from Y into the grade X. We can form the following diagrams. On the left, we have a way of depicting composition of graded morphisms using a diagram in the enveloping actegory. And also on the right, we have a way of depicting the reindexing alpha upper star of F as a composite in this larger actegory. And it can be quite convenient to calculate with these diagrams and also use them to represent and define various things in V-graded categories. And we'll see examples of this in just a moment.
Rory, just a warning that you are entering into question time.
Okay,
So
thanks. So
you can use a bit more time, but you will have less time for questions. So that's okay.
All good. Yeah, thanks for letting me know, because yeah. And so what we're going to do at this time is we'll generalize this notion of weighted pullback that we had introduced in V-actegories. We'll generalize this to this more general setting of V-graded categories, which includes in particular V-enriched categories. And so we can specialize this then to V-enriched categories. So let's generalize this concept of weighted pullbacks to V-graded categories. As a definition, let C be a V-graded category. Let X be an object of V, and let F from X comma A to B and Q from Q to B in C be, of course, a graded morphism and then an ordinary morphism, respectively. Then a weighted pullback of this ordinary morphism Q along the graded morphism F is an object P of C, mimicking what we had earlier, equipped with some morphism P from P down to A, and a graded morphism F prime of this form, making the envelope diagram that we're drawing here commute. And this looks just like the diagram we had earlier, but now this is for a V-graded category, and the diagram lives in the enveloping actegory. And we'll have to ask for a universal property. It won't be just a simple ordinary universal property this time. We need a graded universal property. A graded universal property, let's spell this out briefly. So we throw in a grade, an additional object y of v, and so this is the graded aspect of the universal property. For all r of this form and every graded morphism g of this form, with a grade being the monoidal product, making the envelope diagram of this form commute, so we're just dealing with that additional grade thrown in y. We ask for a unique graded morphism this time, T, of the given additional grade Y from R into P, the weighted pullback, making the following envelope diagrams commute. So still an elementary sort of way of defining this by way of a graded universal property. And then Indeed, weighted pullbacks in V-graded categories, they are equivalently weighted limits for a certain special class of V-hat enriched weights. So these are a special case of V-hat enriched weighted limits. As examples, when C is a V-graded category with copowers, so equivalently a V-actegory, we recover our earlier notion of weighted pullback, which we defined in V-actegories earlier in the talk. But also now we can apply these concepts to V-enriched categories. For example, if C is a V category, then a graded morphism, f from x comma a to b in C, is a morphism as we know of this form, f from x to the Hom object script C a b in V. And then a weighted pullback of a morphism Q down to B along F is given by an object P of C equipped with morphisms of these forms, so P presenting P as an object over A and C, but then a morphism F prime in V into the Hom from P to Q with a certain property. So we can spell out what's required. It's sort of, in a sense, an enriched universal property. When V is biclosed, weighted pullbacks in V categories can be described as weighted limits for a certain class of V-enriched weights. Given a V-graded category, we can define the notion of power in C. A power of A by X is an object A to the power X of C with a graded morphism of this form looking like an evaluation, such that a certain universal property or graded universal property holds. And we can also define conical limits in V-graded categories. These can be described as ordinary limits in C naught, the underlying ordinary category, that are preserved by each of these set-valued Hom functors for the grades X and objects A of C. Then with these concepts, as another example, if we have C being a V-graded category with a conical terminal object, then a power A to the power X is equivalently a weighted pullback of the unique morphism from A to the terminal object along the unique graded morphism of grade X from the terminal object to itself. So powers can be described as a special case of weighted pullbacks in the presence of a conical terminal object. And then also in a V-graded category C, I-weighted pullbacks for the unit object I of V, these are equivalently conical pullbacks. So we recover the ordinary conical pullbacks, or, V-graded conical pullbacks. And then these ideas lead to the following theorem. Let's say we have C being a V-graded category, and suppose that C has powers and conical pullbacks. Then we can mimic the recipe we had earlier now in this V-graded setting, because then C has weighted pullbacks. We can construct them explicitly. The weighted pullback of Q along F can be constructed as the pullback of this form. We're sort of mimicking the same recipe we had earlier, but now in the V-graded setting. So to have weighted pullbacks, it suffices to have powers and conical pullbacks. Now, related to this, we'll introduce a notion of simple completeness of V-graded categories. A V-graded category C is simply complete if C has powers and finite conical limits. So a nice simple thing, that we would have thought of before, simply having powers and also finite conical limits. And we can prove that a V-graded category C is simply complete in this sense, if and only if C has weighted pullbacks and a conical terminal object. Then, specializing this to the case of V-actegories, we'll see simple products showing up again because they're only defined in V-actegories. So as a theorem, let C be a V-actegory. The following are equivalent. Firstly, that C is simply complete when regarded as a V-graded category. Secondly, C has finite limits, just ordinary finite limits, and each functor x dot blank from C to C has a right adjoint, blank to the power x. This is what ends up being required for powers in the V-actegory case, nice and simple in this way. But thirdly, we can bring in weighted, as we had above, again, we have a formulation in terms of weighted pullbacks, namely that C has weighted pullbacks and a terminal object, just ordinary terminal object. And lastly, we'll bring in simple products into the picture. So fourth, C has simple products and finite limits. And that brings us to the end of the talk. Thanks very much.
Thank you. Okay, we have very little time for a few questions if people have any. Feel free to unmute yourselves. Paul?
I forget, Rory, whether you were in some previous life involved in semantics of dependent types in locally Cartesian closed categories and such things.
No, I wasn't. No.
Oh, right. No, I had a vague idea you were. Okay, so Lorvier's hyperdoctrines, which were, in my opinion, vastly overcomplicated structure. We had the quantifiers were adjoints to substitutions over arbitrary maps.
Yeah.
Now you appear to be only talking about exponentials over generalizations of product projections.
Great point. So shall I comment on that? So basically, if we go back to the first setting of the talk, right? Let me just try to get back to the beginning here. So when we go back to the case of categories with finite products, right? We have these formulations, right? So in this case, as you're referring to, here we're discussing right adjoints to substitution along product projections for binary products, as you're referring to, right? Now, the interesting thing is that when we proceed to the actegories case and look at simple products, let's take a look at that for a moment. We could still define simple products in the actegories case, but we do not have product projections here, right? So there is actually no product projection along which to consider substitution. So interestingly, the idea of simple products still, which is a special case in the Cartesian world, a special case of right adjoints to substitution along arbitrary morphisms, namely the special case of product projections. Well, here in the actegories world, the product projections don't actually exist, and yet simple products still do. So this is my response to your comment. Yeah, I hope that illuminates things a bit.
Can I continue, right? So the point of the more general situation is that it's products of dependent types.
Yeah.
Right. Now, this gets a very complicated subject, and we need things like that are called Beck-Chevrolet conditions for making this make sense so that you can substitute under the quantifier. Thomas Streicher showed that the complication of the Beck-Chevrolet condition essentially cancelled another complication which I don't recall in this subject. Now, my involvement was when there weren't the general dependent products, but there were the dependent products in some sort of circumstances. And when you'd introduced the monomorphism, I thought you were going to go in that direction. I put a lot of work into trying to simplify this generally very complicated calculation down to much simpler ones, and it's related to things that were called what was the name? Partial products. It wasn't a very good name, but there's some material about these in the later section of my book, 9.4 of my book. So there may be things there that you could use and to generalize into your situations.
Thanks. Yeah, I would comment. So in a sense, this train of thought, is where things get really interesting with this material, because we can envision, right? I haven't talked about this in the talk, but where I want to go with this, in part, is to consider the relevant notion of fibration, and it's in the world of fibrations. And index categories that the Beck-Chevalley condition becomes relevant. When we generalize these concepts, not from just morphisms down to a base object, but to the more general setting of fibrations, then we actually have to start asking for Beck-Chevalley conditions. And one thing that I found that was quite interesting is in pursuing the relevant notion of fibration here, which is different, because we're dealing with these weighted pullbacks as a kind of enhanced notion of substitution, you can notice that this enhanced notion of substitution, oddly enough, encompasses a certain form of dependent product, namely simple products. And the funny thing is that in the relevant analog of the notion of fibration, no Beck-Chevalley condition is needed. It's sort of taken care of by the fact that, oddly enough, in this setting, the form of dependent product being considered is actually a special case of a generalized form of substitution, which is really odd and unexpected.
Right. You may have rediscovered Thomas Stryker's lemma in that case.
Where is this?
I doubt it's long since gone out of my skull, but if you have a look in my book, you'll find a reference to it, I think.
Great, thank you.
Okay, it's probably time to thank Rory again for his nice talk.
Thanks very much.